Hello, my name is Luke and welcome to this Pytorch tutorial series. So we're up to section 8 in this series. As per usual, you can find all of the tutorial code on my GitHub repo, link in the description. If you like this video, remember to like and subscribe to stay up to date with future videos. So we're now looking at implementations of specific algorithms in Pytorch. We've covered a lot of the concepts and basics of Pytorch and how we can implement deep learning algorithms. And a lot of the concepts we're going to be using in this tutorial today, this video, we've already seen before. Things like logistic regression, CNNs, ResNets, using pre-trained model weights for transfer learning. So I'm going to kind of brush over those. I'm not going to go into that in too much detail. If you're not familiar, you can go into some of the previous videos. So as I said, we're looking at bounding box detection or object detection in this video. Now, object detection is a very useful and a very widespread application of deep learning models where we seek to not only sort of classify or determine what is in an image, but also localize the object within the image itself, right? We're going to look at a pretty simple implementation of bounding box detection where we've only got one object per image, right? You can expand this, of course, to multiple objects per image, multiple objects of multiple classes as well. You may have heard of things like YOLO for object detection, but we're going to simplify it today. So we're going to focus mainly on just bounding box detection, the concepts of that, things like IOU as a metric, as well as how we can implement a Pytorch dataset for bounding box detection, given some dataset we find online. Okay, so firstly, what is a bounding box? Well, a bounding box, as the name suggests, is basically a box that defines the range in which an object lies in an image. So if I were to have, say, a person here, the bounding box would describe the region, a crude rectangle that defines the region in which that object lies within the image. So we're not just giving it a general label for the entire image, saying this is a person, but we're localizing the person now within the image, right? And how do we get our model to do that? As I suggested, we're using logistic regression. But what are we regressing to? Well, there are many things you can regress to, but for this 2D box, we need to define at least 2 points. Now, you can define this top left-hand corner and this bottom right-hand corner, and that is enough to fully describe the bounding box within this image. You can also define this top left-hand corner and just define a width of the bounding box and a height. This is what we're going to be doing today. Either version works. So as you can see, in our case here with a single object, we're going to need 4 outputs of our model, the coordinates of the top left-hand corner of the box, as well as the width and height of the box. So in case you're unaware, the coordinate system of our image, X is increasing in this direction and Y is increasing in this direction, which means this top left-hand corner here is coordinate 0, 0. All right. So hopefully that will make sense what our bounding box is and how we describe it and how our model will produce it. In our specific case, we're going to give the coordinates as relative coordinates. What that means is that we're going to divide the coordinates by the actual height and width of the image. So if this is, I'm going to say x, y, 0, 0, then this coordinate, this last pixel here, is going to be width, height. Technically, it's going to be width take 1, height take 1, but hopefully you can get my point. By dividing the pixel coordinates by the width and the height, this last coordinate will be 1, 1, or 0.999, but it'll approach 1, 1 for here. So relative pixel coordinates. And because all of our values can be between 0 and 1, we can use logistic regression for this problem. So the coordinates are going to be between 0 and 1, and also the width and the height. The height and width are never going to be larger than 1, 1, because that means it's going to be larger. The object is larger than the image, and we're going to assume that's not going to happen. Okay. So let's go back. Yeah. So now we're going to introduce intersection over union as a metric for determining how good a bounding box prediction is compared to some ground truth prediction, and why we'd use that. You might think, if we're using logistic regression, can't we just use the loss as a metric for how good a bounding box prediction is? And you can do that. However, there is one issue. First issue that might arise is that, if you're not normalizing the pixel coordinates, well then larger images with, larger pixel coordinates, and more pixels has a higher range of pixel values, then, the loss might be bigger for bigger images and smaller for smaller images. But that's not a problem in our case. But the problem that remains is that the loss does not provide a good way of really quantifying how good the bounding box is in terms of objects of different sizes. So let me just clarify what I mean by giving you an example. So let's say this is my ground truth in blue, my bounding box, and let's say we have a prediction in red. Let's say this is my bounding box prediction in red. You might look at this and say, okay, it's not perfect, but it's pretty good. And maybe we can use, if I'm predicting this value here, so that's my ground truth, and this is my prediction here. You can see the height and width are pretty much the same, so maybe the loss or the difference between them is 0. We've only got this difference here, right? And it might be pretty good. However, let's consider a different case where our objects are quite a bit smaller. I've got my ground truth here, and my prediction here. Now you might look at this case here and say, well, that bounding box prediction really is not very good, right? Even though the actual difference between the predicted coordinates is pretty much the same. It's almost the same, right? And if these bounding boxes were even smaller, the object was even smaller, comparing, maybe the bounding box here was really large, the bounding box here was really small, their loss, the difference might be exactly the same, but it's not very effective as an actual bounding box, right? This bounding box here might be usable because it gets most of the object in its bounding box, but this one here, you can see it gets far less. It gets like a quarter of the object in its actual bounding box, while this gets a much larger amount. So that suggests that what we need to do is we need to make or come up with a metric that is agnostic to the actual size of the object. As I kind of hinted at there, what we need to do is somehow divide by the area or the size of the object, divide out the actual size of the object. And that's basically what intersection over union aims to do. So intersection over union, or IOU, you commonly see it written as, if I just quickly label this as A, this is B, this is equal to the area of A, or the area of the intersection of A and B, divided by the area that is defined by the union of A and B. So this area here, this intersection, is basically the overlap between the two bounding boxes. The union is the total area described by not the sum of the areas specifically, but defined by the border created by both of the bounding boxes. And that's important, right? This total area, right, defined by both bounding boxes is the union, right? So I take this intersection area and I divide it simply by the total area defined by both bounding boxes. And we're dividing an area by an area, so we have a unitless quantity. And you can think of this as basically the percentage of the intersection, the percentage of, that intersection that is, the percentage of the bounding boxes that is the intersection, sorry, right? In that case, we're looking at percentages, and we basically will get different IOUs depending on the size of the bounding box. So we're not looking at the difference between the coordinates, we're now looking at this area of overlap, the percentage area of overlap. Okay, so hopefully you can see why that's beneficial. So it doesn't matter how big the object is, we get a sort of relative metric. So I'm going to split screen this section, and we're going to go through just how we can implement that in Pytorch. Okay, so this class here, we're going to pass this to the trainer and use it as a metric for, use it as the metric for our model, right? So as I mentioned, the output of our model is going to be 4 values, the min x, min y. Min just means it's going to be this top left-hand corner, not the bottom right, which will have max x and max y. So the min x and y values of the bounding box and the max x and y values of the bounding box are here. So that's the sort of range the bounding box lives in. Sorry, I skipped y. Specifically, we're going to be using that. Let me just quickly cover that now. Basically, it's just an easier way of assuring that the second set of coordinates, so if I had x min y min x max y max, defining this top left and bottom right, it basically makes the calculation of the IOU a bit easier because we are guaranteed that this second set of coordinates the model produces is always going to be larger in x and y than this one. At the start of training, you can imagine there might be the case where this is actually, over here, sort of backwards. And in that case, you'd have to have additional checks in your IOU calculation to make sure it's a valid bounding box by constructing the bottom right coordinate from the top left with the height and width. We can always sort of guarantee that it's a valid bounding box. You may have the case where this coordinate ends up being outside of the image. While that's not really a valid bounding box, it doesn't change or doesn't really affect the IOU calculation. We still get a valid IOU calculation. Right. But for the IOU calculation, we still need the y max and y, so the x max and y max. But we're constructing it again from the x min and y min. Right, so that's what we're doing here. The next thing we're going to do is we're going to find for this top left-hand corner, which of the 2 points is max in both x and y direction. So here you can say xa and ya. So that's referring to the first value for the ground truth in the prediction, which is x min. And what I'm saying is which one of the 2 values, the predicted, which is in red, or the ground truth in blue, has the larger x value. Remember, x is increasing this direction, y increasing this direction. So which one of these has the larger x coordinate? Well, the red, our prediction, has the larger x coordinate. And so that's the value I'm going to take. Sorry, I should clarify. The first step we're doing here is trying to find the area of this intersection. Sorry, I did skip that. Once we find this area, it's very easy to find the area of the union, right? The area of each of the bounding boxes is very easy to calculate. It's just the height times the width, which we get from our model, we get from the ground truth. And then we also need to subtract the intersection, but we'll get to that in a second. So the first step is to find this intersection, right? And we're going to find that by getting the top left and bottom right coordinates. So the first thing we're doing is finding this top left coordinate. So we've got max x for these coordinates. It's this one here. And then we do the same with y, right? Max y. And you can see it's also this point here. So you can see the top left-hand corner of our prediction is also the top left-hand corner of that intersection area. Now, the next thing we're going to do is we're going to find the coordinate of the bottom of the bounding box using the bottom of each of the predictions and the ground truths. And we're going to do that by finding the min x and min y between them. So you can see that this coordinate here has the min x, also the min y. So this is a very simple case. That's very easy to find the min and the max, right? To find this intersection area. So from these 4 lines here, so I've done this in a batched way. So we're concatenating the prediction and target x and y values and using max over the dimension that we concatenate, which is that second dimension. That will return the arg max as well as the max values. We'll return the max and the arg max. The first one is the max. I don't care about the arg max. And I'm unsqueezing to make sure we have that additional you can see it here, that second dimension. So it's always going to be two-dimensional, which is useful later on. Okay, once we have those 4 values defining these 2 points, we can calculate the area of this little rectangle in here, this intersection area. And that's simply going to be the x-coordinate of the larger point. So we're going to basically find the height and width of this box. So we take the x-coordinate of this bottom right, which is the max x value, and we're going to subtract it from the x value of this top left, and that'll give us the width. And we do the same thing with the y, and that'll give us the height. And then we multiply the height by the width, and we get the area. You can see we've got a ReLU in here for our x length and y length. And that is to ensure that we always get a valid area or a valid length, right? It's to capture an edge case. The specific edge case is if there is no intersection. There is actually no intersection. So if we don't do that check, we'll actually get an invalid area. To illustrate why, let's see what happens if there is no intersection. So between this value and this value, which one has the larger x? Well, it's this one here. Which one has the larger y? It's also this one here. Which has the smaller x and smaller y? Well, that's the smaller y, and this is the smaller x. And so these points define this area in here, right? But you can see that the point B here is here, and the point A is here, right? And so if we subtract the x value from here to here, we're actually going to get a negative x value, because this is B, which is smaller than A. Sorry, B is smaller than A. Yeah, so B subtract A is going to give us a negative value. So if we ever get a negative value, the same thing can happen with y. If you move these around, if you ever get a negative value for the length, that means there is no intersection. And so I can just ReLU that, which will just 0 negative values, and you multiply 0 by something, you get 0. So if we ever get a negative value, the area of intersection is going to be 0. Okay. The next step, once we've got that intersection area, is to just calculate that total area. Like I said, it's this area here bounded by this green line here. And how we can calculate that is just to sum up the area of each of the individual bounding boxes. Now, if we just do that, what we'll get is we'll count this area in the middle twice. So we count it once for box A and once for box B. So to get the area defined by this green line, we need to subtract this intersection area once, right? That'll stop us from counting it twice, which is what we do here. So we calculate the area of each of the bounding boxes. I'm using the original XY height width and just taking the height and the width and multiplying them together to get the areas of each of the bounding boxes. We sum them up, subtract the inter area, and we divide the inter area by that value. I'm also adding a little offset here, just in case this ever becomes 0, though I don't think it can. Yeah. This will only be the case if the bounding box predict the ground truths are ever 0 area, which they can't be. But yeah, just in case. Okay, so this will give us a batch of IOUs. The IOUs are going to be values between 0 and 1. Again, think of it like a percentage, right? And this is an n.module class, and it has a forward function. I'm going to use that forward function to basically define how to get the actual metric values. It's going to take in the predictions from our model, as well as the data tuple, and you'll see that later on, this data tuple. The actual target bounding box is the second value in that data tuple. And the raw outputs of my model, I'm going to assume I haven't sigmoided them yet. Again, we're doing logistic regression, so I need to put a sigmoid. And I'm just taking the first 4 values, just in case if you wanted to modify this and say add class activations as well, right? But in any case, I take both of those, put them into my IOU calculation, and we return that. Like I said, we get a batch of IOUs, and when I actually log it, we'll take the expectation of that, or the average of all those IOU calculations. Okay, so that was our IOU calculation. So as I said, I create an instance of this and pass it to the actual trainer as our evaluation metric. If I go into my trainer, you can see during evaluation mode, I've called it epoch accuracy, it's technically IOU, but I put my output of my model and the data tuple into that model. I take the sum, so we're summing it up, and then when I actually log it to the accuracy logger, I divide by the total number of data points. Okay. So I'm just going to run the code up until then, and we can move on to the next point. So the dataset we're using is this Cub 200 dataset. The dataset is hosted on Kaggle. If you're not familiar with Kaggle, it's a great website for datasets. They also have competitions and the like. And you'll need to download this dataset, right? 2 gigs to download. I think it unpacks to about 7.5 gigabytes. And this dataset is basically a dataset of pictures of birds and has bounding box predictions. It also has class attributes as well. So you can see we've got each of the images organized into the species. So you could do classification with this as well. It also has segmentation masks, which we're going to use in the next video when we look at segmentation. But for our case, importantly, it has the bounding box coordinates. These bounding box coordinates, as you can see, are in X, Y, width, and height. Right, that's X min, that's our Y min, and our width and our height of the bounding box. You can see they are in pixel coordinates. So we're going to divide by the max width and height. Okay, so we need to download that. It downloads as a file named archive. I think I just renamed that to Cub 200, so you can extract that. Make sure when you go into it, you extract each of these folders within that zip file. Just extract everything. And I renamed archive to Cub 200. You can put that in the datasets directory in this repo, or you can just make sure dataset root points to the location of the dataset. Okay. So now let's move on to how we can actually build a dataset loader or a dataset class in Pytorch for this dataset. One thing you're going to need to install additionally is this Albumentations library. This is what we're going to use to perform the data augmentation, right? And we need to use something a bit different. We can't just use the basic Torch Vision augmentations, because we need to ensure that any augmentations we apply to the image are also applied to the bounding box detection, the bounding boxes themselves. If I have some image and I sort of rotate it or flip it, I need to make sure the bounding box rotates and flips as well. Now, Pytorch does have new Torch Vision v2 transforms, as some of them in beta that will do this as well, but they're currently in beta and they're a bit limited. But Albumentations, which is not specifically a Pytorch library, but is a data augmentation library that will augment images, bounding boxes, as well as segmentation masks as well. So that's what we're going to be using, and we'll show you how we do that in a moment. So let's have a look at our dataset class, which you should have. Right. The first thing we need to do, I'm going to use pandas to read in the image class labels, the images text file, as well as the images bounding box. So if I go into the Kaggle, you can see what we've got is we've got kind of separate text files for everything. This images.txt basically gives us a file name and sort of file path directory from images and an index. So it basically indexes each of the files. And what we do is we use that index to index, say, the bounding boxes. So that index corresponds to the bounding box. We're also going to use the image class labels as well. Right. We don't need to, but we're going to. Yeah. So these are text files. They're not really CSVs, but we're going to use pandas anyway and specify the separator as just a space. We're also going to define the column names as index and class. So this is the class labels. And for the actual image index and file path, we're going to do the same thing, index and file path. And also with the bounding boxes, the index, the x, y, height, and width. So if we go to our bounding boxes, index, x, y, height, width, all separated by a space. Right, and we're just going to make sure we define the column names and that the index one is all named the same thing, index. Now the test train split, there is a test train split in the actual data set, but I think it splits it like 50-50 test train. I wanted to be a bit more, give it a bit more training data, so I made my own one. It's named and organized exactly the same, except it's located within the same directory, the solution, so you should have that as well. But I named it and formatted it exactly the same as the actual data set. Again, index and split. It's just a 0 or a 1 for test or train. And then we're just going to merge those data frames on the index. So we're merging all of those independent data frames together, lining them up based on the index, right? So now we should have index, file path, class, bounding box, and test train split. This line here, we're just removing any lines based on whether or not they are in the test or train. So if test train is 1, then we're removing any lines where the test train value is not 1. So this is the way we're splitting our training and test data. Right, and we've got some additional flags here. This data set is also going to be used in our segmentation one. So we also have a flag saying, do we want to return the segmentation masks? For our case, it's going to be false. We don't want to do that. Okay, so let's look at the interesting part. First thing we do in our get item function is get the file path of our image. We also get the actual label of the class, but that's not important for now. We're going to use CS OpenCV image read to actually read the file path. And once we've got our image, we're just going to make sure it's RGB. Okay. This class here is basically, this function here has 2 jobs. It has the job of dividing the actual pixel coordinates of our bounding box, making them relative divided by the image size. It also checks whether or not the bounding box is a valid bounding box. So we're checking that the top left and bottom right coordinates are within the image dimensions. Now you might think, why do you have to do that? Some data sets, this one included, don't really have valid bounding boxes, or have the case where the bounding box could go outside of the actual image, right? The problem is that Albumentations doesn't like that, so we need to check that whether or not that's actually happening and remove the ones. So I should specify this one here is the function looking at get bounding box list, is checking whether or not the bounding box is outside the image size. Get output tensors is used later on. Sorry about that. So data here, again, this is a pandas data frame, and we're just indexing that to get the XY height width and putting that into an array and doing the check. That's how we get our bounding box array. This is just a list. So return masks is false in our case, so we'll skip that and look at the last one. Again, our transforms here is Albumentations transform, and the way we ensure that the same transform is applied to our images in our bounding box is by just telling it that we have some image and we have a bounding box array, and it will perform the transform on them all together. Now, this bounding box array here, you'll notice that this is actually a list of lists because Albumentations can handle cases where you have multiple bounding boxes per image, right? And it will do the augmentations on all of those. We also pass it the class labels as well as a list. I think it's just a list. And what Albumentations will do is, if it performs some transform and the object is now outside of the image, it will remove that object from the list. That's why also in get tensor outputs here, I'm checking to see whether that whether or not this is empty, and I'm just making sure that it has some sort of valid values there. But in that case, that's as simple as it is. This will return, I think, a dictionary. The implementations will return a dictionary, so we just need to index the image, bounding box, and label, which I do in this get output for the bounding box and the label, and we just return that. Okay, so let's have a look at the transforms that we're using. So smallest max size here is just making sure that the max size, this is the smallest size of our image, so it might not be square. The smallest size is image size, because some of our images are sort of rectangular, some are quite stretched out, odd shapes. So we're resizing that so that the smallest size is the image size. And then we're then doing a random crop. So we're then cropping that to make sure the height and the width is square, image size by image size. Horizontal flipping, we've seen it again, but this time the transform will make sure that the bounding box gets flipped as well. Scale, shift, rotate, similar to what we've seen, randomly scaling, rotating, and shifting. But again, it will just make sure the bounding box is also shifted by the correct amounts. And then the next few don't really affect the bounding box. RGB shifting, changing the colors, changing the brightness and contrast, and then normalizing like usual. And finally, the last one here is the only really Pytorch specific transform. You can see it comes from a different submodule of the library. And this is just to make sure that the returned object is a Pytorch tensor. So we can just return it from our dataset, get item function. And we also need to define some parameters. The format of our bounding box is the Coco dataset. So define that. Min area, min visibility just says, I've just set these as 0 just to get rid of them. Basically, how small does your object need to be and how much of the bounding box needs to remain on the image before we get rid of it. So I'm just saying, I've sort of scaled these to make sure that would never happen, that the bounding box would never, or the object would never completely disappear from the image. But if you want to say, okay, well, if the object gets too small, get rid of that bounding box, or if the object is off the image so much, then we can get rid of it. Right, so basically, at what area do you want to have a cutoff? At what percentage do you want to have a cutoff for the actual object if it's off the image? All right. And then our test transform is just going to be the same thing, but without the sort of random operations. Okay. So we create that data set here, passing in the parameters, test and train, and we're going to split the training set again to a validation split as well. We're going to be using ResNet34 with the pre-trained Pytorch ImageNet weights, V1, and same as we've seen before, we pass it all into our model using a binary cross-entropy loss with logit. So we're doing our regression as I mentioned. Output size 4. So the actual trainer, not sure I mentioned this before, the actual trainer will do the removing the last fully connected layer of our model and replacing it with a new one, which is what happens here. And that gets called in our initialization function. So it'll do that automatically for us. Okay, we set our data, and as you can see, we've got our data here. This is our test data of the different birds. We can see what our bounding boxes look like. We're using the Torch Vision utilities, draw bounding box. This expects a xmin, ymin, xmax, ymax, not in relative coordinates, so the actual pixel coordinates. So we're just converting our labels to that format and just drawing a green bounding box on that. It also expects the values to be unsigned 8-bit integers, so the pixel values. And we get our bounding box of our bird. Okay. So let's now train our model. So ResNet34 is 21 million parameters, and let's train. So this will take a little bit of time. I'm training for 50 epochs. That might be a bit too much, but we'll get back when it's done. Let's just wait till there's a first epoch. First, I'm evaluating the training sets separately to the actual training loop. You could do both at the same time, but I'm doing them separately to get a sort of more accurate value. So you can see our IOU is already up at 0.71, so it's already relatively good, but we'll see how much better we can get. All right, so our model has finished training. Let's look at our results. So first thing you'll notice is that the training loss, while it does decrease, it doesn't decrease that far, and it kind of converges pretty early on. It is sort of decreasing still a little bit, but it's kind of hard to actually tell whether or not the model is improving. So you can see our validation IOU was 0.83. So let's have a look at bounding box predictions and the actual IOU. So you can see the actual IOU, our training IOU, and our validation IOU are actually continuing to increase over time. So this kind of tells us that the training loss, again, is not a really good indicator of performance of our model. You can see there is a bit of overfitting here. Maybe you want to increase the type and number of augmentations or something like that to prevent that. But you can see performance is still improving. Even our validation seems to be improving a bit. Again, like I said, that's probably because we have different birds of different sizes in our data set, and while sort of general location of the bounding box might improve quickly, the sort of fine tuning and moving of the box to the correct locations to the IOU improves happens more slowly and is less noticeable in the actual loss. So we can have a look at the predictions versus the ground truth. So the predictions are in red, the green is the ground truth. So you can see it gets it more or less accurate for our test cases. Some better than others, but this is more than useful, more than usable for specific applications that you might have. Like I said, you could improve it further. Good. So you can play around with this, like I said, to try and improve performance. But hopefully you got an idea of how you can construct your own, or how these systems work. So let's just finally run test. So 0.83. So IOU is relatively good. Again, perfect IOU would be 1. So converge to 1 eventually. So as I mentioned at the start, this is a very simple bounding box detection. There's only one object per image. You can expand this for multiple objects. That's what YOLO does, and multiple other earlier versions, but you run into multiple problems. If you don't know how many objects are actually in your image, you don't know how many bounding boxes to predict, right? So those more advanced techniques add additional steps, additional outputs in order to do that, in order to predict multiple objects in your actual image. And like I said as well, you can go further and also produce a classification per bounding box. So you could have multiple different bird species in a single image, get a bounding box for each of them, and get a class prediction for both of them. So that's what these more advanced methods do as well. If there is some interest, I can show how you would implement something like YOLO from scratch, or just show how you can implement some existing YOLO models as well. But that's all I wanted to go through today. Hopefully you found that interesting. If you did, remember to like and subscribe, and I'll catch you in the next one.